putting up with it. But here we are, streaming, and we are live, and let's get to it. Okay, so in and of itself, atoms are not the most exciting thing. By and large, most of the things in the world around you are not just one atom. They're not just a single thing. There are things that are. If you collect the soot in the bottom of your fireplace, that's mostly pure carbon. Things that are made out of metal are sometimes made out of just a single metal. Well, even then, not usually. But, you can get something that's iron, and it is just iron. Aluminum is a big one. That's something we use where it's just aluminum. You get aluminum foil. Those are all aluminum atoms. But most of the things you interact with are mixtures of different stuff. And at bare minimum, most of the things you interact with are compounds, which means they're atoms that have been stuck together in key ways. We are in one period going to talk about compounds, but compounds are really all of what chemistry is. So this is just dipping your toes into chemistry. That's all we're doing this year. We're just dipping our toes in and we're going, okay, the water's nice. And then in grade 10 we'll do a bit more. In grade 11 we'll do a lot more in chemistry, and I hope you do. And in grade 12 we'll do a lot more. I hope you take that. Those are great courses. So this is just simplicity. Now, the main thing I want you to understand is that compounds form because compounds have to form. So atoms come together and stick to each other because they have to, because, and you might find this models your own life, left to themselves, atoms are not very stable. When you're on your own, they're not very stable.
Music video.
Oh, thank you. Oh, perfect.
I don't know if I'd be playing it live, but that's just me.
Sorry?
I don't know if I'd be playing it live, but that's just me.
All right. So there we go. So the reason we have to make compounds is that atoms can exist on their own, but as a rule, they don't exist on their own very well. And I'm going to use an analogy, and this really is an analogy. But does anyone here do like car work? Anyone help their mom or their dad and work on the car a little bit maybe? Okay. Usually you got a couple in there. That's all right. Anyone ever been around when you get new tires put on your car? Anyone ever seen that? Either done it yourself or gone to the shop and had them do it? I see some people like looking at screens here. There's no screens to be looking at. I'm talking about this. Pay attention. It's important stuff. This is complicated stuff. So when you go to get new tires put on your car, put the tires on your car, but before they do, they put the tire on the wheel, and then in most modern tire shops, they put that wheel on a machine that checks to see if it is balanced. What's that mean, if it's balanced? Sorry? Equal. Yeah, equal in weight. Because if one side of the tire is heavier than the other, as it spins around on the road, what do you, the driver, feel? It's going to shake, right? Can you imagine that? If you have a tire and one side of it's heavier than the other side, as it spins, it's going to shake, right? It's going to vibrate. And if that's bad enough, it'll actually spin itself right apart. If you have a badly unbalanced tire, it'll actually damage the tire because it's just so much vibration. Can you kind of picture that? So you can actually check this on your cars. When they go to balance a tire, they just have little metal clips that they'll put on one side to balance it out. And my tire has a couple of these on. They just put them on and they put them. The machine tells them where they need to put it to make the weight equally distributed. And you put on, and now the weight's equally distributed. And now it can spin around, and it does so in a stable way. And if you ever knock into a curb, which you'd never do when you drive because you'll be good, careful drivers, but say you did, and you throw a tire out of balance, you'll feel it on the road. I mean, you can feel the steering wheel in the car shake while you drive. It has to be balanced. I have in the lab something called a centrifuge, which takes test tubes full of liquid and spins them really, really fast. Again, I see some people on computers. Let's just shut down for a second. It's a key concept. All right? Pay attention. So when we take these test tubes and spin them really fast, if you don't load, it says right on, there's a big warning label on this thing that you have to load it equally. If I put a test tube on this side, I have to put one across from it that's equally full. It has to be balanced. And if you spin this thing without it being balanced, it will become damaged. Does that make sense? Because it spins these things so fast that if it's not balanced, it'll shake itself apart. It tells you right on there, warranty void if misused. Does that make sense? They won't fix it for you because if you use it wrong, it's going to break. Atoms are similar because, and this is an analogy, all right? This isn't a perfect, I'm not explaining the actual physics to you really, but if you think of it as an analogy, you've got the electrons spinning around the nucleus, and they're moving really, really, really fast. Can you picture that? And if you don't have a full shell, that shell isn't balanced, and as they spin around really fast, that atom is unstable. Does that kind of make sense as a concept? So an atom that doesn't have a full shell isn't perfectly stable. Now here's the problem. Looking at the periodic table, do most of the atoms have full shells? No. In fact, what are the only atoms that have full shells?
The last of each row.
Yeah, the last of each row. These ones here all have full shells. All right, so an atom can only be fully stable if it has a full outer shell of electrons. So an atom can only be fully stable if it has a full outer shell of electrons, and most atoms don't have full outer shells. So atoms have to come up with clever ways, and I mean not clever at all. This all happens as a result of just forces interacting. The atom isn't sitting there thinking, how do I get a full shell? But we kind of talk that way. They have interesting ways of handling that. Metals have a really funky thing where they just pool all of their electrons together in what we call this continuous syncytium of electrons. They move from one to another and they do weird things, but every atom has to come up with a way to get a full shell to be stable. Does that make sense? So what are the only things that are all on their own by themselves stable? Only these guys. Only what's He? Helium, neon, argon, krypton, xenon, radon, and I always forget what OG is. Oz. What's OG? Can someone tell me? Can someone look at the periodic table?
Organdon.
Yeah, I don't know. Anyway, those are what we call the noble gases. They're called noble because, like, noble people, like kings and queens, they're snooty and they don't interact with other things. These are stable all on their own. So the noble gases are stable all on their own. And we're going to make a note of that. We'll say the last column of the periodic table have full shells. And are stable on their own. And they're called the noble gases. So that last column of the periodic table, they have full shells. We call those the noble gases. But every other atom on the table can't be stable by itself, and so it needs to find a way to become stable. And that's what we're going to talk about in this lesson. So I'll give you a minute to write that. I don't want to rush you. If I'm going too fast, let me know. I get excited about this stuff. I find this stuff exciting. There should be a comma in this hilarious and witty title. Come on. Who taught me English? That's the real question. I gotta say, that's a pretty good comma I drew. A plus. So, like a tire has to be balanced if it's going to rotate, the electrons in an atom have to be balanced. You have to have full shells of electrons for them to be stable. A very small number of atoms already have that. That's one of the reasons we use helium in a balloon. Like, you ever see, like, you know, like before football games, they have the big blimp, they call it the Goodyear blimp, that thing? It's full of helium. And they picked helium because helium is really light. It's really, really light. Every single atom of helium only has 2 protons in it, and I believe helium has 2 neutrons as well. Can someone check the periodic table for me there? What's its weight? Is its weight 4? Sorry? Weight of 4? 2 protons, 2 neutrons. So helium is really light. So they fill the balloon up with helium because it's so light that it floats. Is helium the best choice for that? The lightest thing you could put in a balloon to make it float? Is there anything better? Ah, good. What is the other option? Hydrogen. In fact, hydrogen's not a little bit better. Hydrogen is way better. It's way lighter. Way, way, way lighter. Helium, every single atom weighs 4 atomic mass units, right? Hydrogen, how much does each atom weigh? Just 1. It is 4 times lighter. Hydrogen is way better at lifting things up. It's 4 times lighter. You fill a balloon with hydrogen, that thing will really lift up. Hey, we used to do that. That used to be a thing we did. What's the problem with that?
It's flammable.
Yeah. Has everyone heard of the Hindenburg before?
Yeah, I have.
Famous disaster, famous, awful, horrific video footage of like people dying in a horrible fire because helium is pretty light. But the other thing about helium is, what do we know about helium? It is really stable. And it's stable because every single helium atom already has a full outer shell of electrons. It's balanced. It's stable. So helium, you try to light helium on fire, not happening. Won't burn. You try to react helium with metals and make them rust or something, won't do it. Nothing. It is stable. It doesn't want anything from any other atom. It's already got a full shell. Does that make sense? Hydrogen, much better lift, 4 times lighter, but does hydrogen have a full shell?
No.
No, it's got 1 electron, and it needs 2 to have a full shell, or it could lose the one it has. It has to do something. It has to do something, but as it is it stable? No. And so hydrogen is scary stuff. Just a little bit of heat applied to it, enough energy, and it starts reacting. It starts figuring out ways to get those electrons. Does that make sense? All right. So that's what we're going to talk about today. We're going to talk about how they come together. So, for atoms that aren't stable, they become stable, well, when you can't do something on your own, what do you have to do?
Get help.
Yeah, you gotta get help. You gotta get help, all right? I'm renovating a bathroom right now, and when I go to put the drywall on the ceiling, which I did last night, I don't have the tools. You can get a tool to do that yourself, but I don't have it. I don't know the hydraulic lift for. So, have I in the past done that by with one hand in my hand pulling the drywall up and the other hand screwing it into the rafter? Yes, I have done that. It's not a fun way to work. What did I do last night?
Get help.
I said, son, stop playing video games. You're drywalling with me. And he said, "Rrr," and I said, shut up, come on, we're doing it. And he was mad at me. But that's it. That's what we did. I got help. When you can't do something by yourself, you got to get help. And for atoms, when they can't be stable by themselves, the way they become stable is by pairing up with, partnering up with, forming a bond with another atom. That's how they become stable. So the goal is, I don't have a full shell, you don't have a full shell. Is there a way that together we could both have full shells? Does that make sense? So what do? Well, let's talk about it. So first we're going to say that. Atoms form bonds This is kind of the foundational theory of high school chemistry. The chemistry at the level you're doing it. The basic principle is atoms are trying to get full shells of electrons, and to do that, they have to partner up with other atoms. This is everything you're going to learn in high school chemistry can be explained by understanding it that way. If you understand that idea, you'll be great in grade 9 science, you'll be great in grade 10 science, you'll be great in grade 11 science, and then in grade 12, you'll start to look at me and be like, Orlando, did you lie to me a little bit? And I'll have to admit, I lied to you a little bit. I didn't lie to you, I kept it simple. So we are keeping it simple right now, but that's the basic idea. Okay, here we are. Now, there are two main ways that atoms can do this. There's actually a lot more than just two ways, but we're going to cover the two biggest ways that atoms pair up to become stable together today. Normally each one would be a full day and we'd do a lab and this or that. We've got to kind of rush through this. So I apologize if this feels like a lot of material coming quickly. We're going to make it work. You guys are clever people, but it's tricky. So, the first thing they can do is give and take. Give and take. And to do that, I want to look at sodium and I want to look at chlorine and how they can become stable. And what I want to do is let's draw Lewis diagrams of each. So I picked sodium and chlorine. This is a classic example because it's an easy one to see. So we're going to draw some Lewis diagrams of sodium and of chlorine. Can somebody remind me what's a Lewis diagram? It's like a Bohr-Rutherford diagram, but am I going to draw, for sodium, am I going to draw a nucleus and say that there are 11 protons and however many neutrons? Do I do all that? No, when we draw a Lewis diagram, what do I do? Awesome. So for sodium, what's the symbol for sodium? Na, good. And if we go look at the periodic table, we know that sodium, how many shells does sodium have? Yeah, it's got 1, 2, 3 shells of electrons. That first shell is full, second shell is full. But in the third shell, how many electrons does it have? Just 1. Is it stable? Is that a stable atom? No. In fact, it's really unstable because it really doesn't have a full shell. What would it need to have a full shell? 7 more. All right, it is not stable at all. And then, what's the other one we're talking about here? Chlorine. What's its symbol? Cl. And let's take a look at chlorine. Where do we find it on the periodic table? Also in row 3, so it also has full 3 shells. 1, 2, 3, and there's chlorine. How many electrons in its outer shell? 7. Is it stable? No. But it's really close, right? It has 1, 2, 3, 4, 5, 6, 7 electrons. Okay, so here's the thing. Not stable. Not stale. Not stale. They're fresh. These are the freshest, only the freshest atoms for you guys. Okay, there we go. Not stable. Don't judge me. All right, there we go. So these are not stable. But what can happen? How could they become stable? Listen. This one, is it going to get up to a full shell? You would have to do a lot of stealing, wouldn't it? Does this make sense? Like, if you're sodium and you're trying to fill that shell, how many electrons would I have to go steal from other atoms? 7. Is there an easier way for sodium? What could sodium do?
Do they fuse?
Sorry?
Do they fuse?
Well, we'll talk about that. So sodium needs to get a full shell of electrons. And right now, it's far, 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 far away. It's only got 1. But what's underneath that shell? And that shell is full. So what could sodium do? What could sodium do? Yeah, it can lose this electron. If sodium loses this electron, if it just says, hey, this electron here, it's going to go. It's going to go away. Then what we would end up with is sodium with its outer shell empty. And because its outer shell is empty, it doesn't have a partial shell. Hey, if it doesn't have a partial shell, it's going to be stable. Now here's the thing. It used to have the same number of electrons and protons, so it used to have no charge. But what did it just lose? An electron. What charge do electrons have? Negative. So it lost a negative. It used to have the same number of positives and negatives. Now it's a negative shy. So what will be true about this now? Good. Very good. That's a tricky concept. But if you give away a negative, you become more positive. Does that make sense? This is true in life as well, by the way. When you get rid of negative things, you become more positive. And the way we show that is this. For whatever reason, to show something has a charge, we put square brackets around it, and then we just put the charge up here. And this would be a charge of +1, because it now has one more protons and electrons. Does that make sense? Tell me if it doesn't. Now here's the nice thing. Sodium is getting rid of an electron. Cool. Hey, do we know anyone around here who could use an electron? Take a look. Chlorine could use an electron right there, couldn't it? Because if chlorine got that electron, how many electrons would it have in its outer shell?
8.
And 8 is a full shell. So does this work for sodium? Yeah. Does this work for chlorine? Seems pretty good. And so now when we draw chlorine, it's got its 7 electrons it started with. 1, 2, 3, 4, 5, 6, 7. And it's also got that electron there that we got from sodium. I just drew them in different colors so you can see where they came from. You don't have to draw them in different colors, but does that make sense? But now, sodium is a +1 charge because it lost an electron. Chlorine now has one more electron than it used to. It used to be a neutral atom. Now it's got an extra electron. What's it going to be? Negatively charged. Does that make sense? And how do I show that it has a negative charge? Well, how do we show something has a charge? What's the rule? What do we draw around it?
Square bracket.
Yeah, we kind of draw these square brackets. Oh, didn't want the green. We draw square brackets around it, and what will its charge be? -1. Now here's the cool thing. Sodium lost an electron, so it has a positive charge now. Chlorine gained an electron. It has a negative charge. And they're both now stable. They both have a full shell. Sodium has a full shell because it doesn't have a partial shell. It lost its partial shell. Chlorine has a full shell because it filled up its partial shell. So they're both stable. But here's the other thing, and this gets to what you asked. You asked me if they do what? If they fuse. Why do they fuse? These aren't fused because like somebody goes and ties a string between them. Why are they stuck together? Because they are stuck together now. Now that we have done this, that sodium and that chlorine are going to be stuck to one another and they're not going to want to go anywhere from one another. Why? Opposite charges attract. Opposite charges attract. If you take something that is negatively charged and put it near something that's positively charged, they attract. Normally you would know this really well because normally we would have already done our physics unit where we do this by charging stuff up and then holding them near each other and seeing do they get close or far. At a bare minimum, if we were in the lab right now, I would do that by charging 2 balloons and showing that the balloons repel each other if I charge them both with the same thing, but if I charge them with different things so they have opposite charges, I can make them go near each other. I can't do any of that here right now, but opposite charges attract, and so now they stick together. So, these are both stable. And I will give you these pictures. I'll just copy them over. Both stable and opposite charges attract. And we call this an ionic bond. We call it an ionic bond because an ion, if you remember, is what we call an atom that has a charge. If an atom has too many electrons or not enough electrons to be neutral, then we call it an ion, either a positive ion or a negative ion. So in this case, this is an ionic bond. So I'm going to write just a quick note about this. So Atoms with only a few valence electrons can get rid of them to avoid partial shells. I'm going to need a few more lines here. So let's see if I can do that. That didn't work. It didn't work at all now, did it? There we go. On the other hand, atoms with almost full shells So this is a lot of wording, I know, but just give it a second, we'll write that, and we'll talk about it. So, a lot of writing there, take a minute and write it, but don't stress about the wording, it's the idea that's important, which is, if you have an atom that just has a few electrons in its valence shell, 1, 2, 3, it's easy to lose those. If you have an atom that has an almost full valence, it's easy for them to just pick up a few extra. This way they can either empty out their partial shell or fill up their partial shell. And either one of those works as a solution to being stable. If you can get the shell empty, great, now you're stable. If you can get the shell full, great, now you're stable. Either one works. But when you do that, you end up with one thing having gotten more electrons, it has a negative charge, and you end up with another thing having lost electrons, it has a positive charge. And because opposite charges attract one another, these two things are now stuck together. And we call that an ionic bond. Key concept, important concept. Yeah, okay, so this is not what we're doing. Yep. Yeah, you should listen to me. That's what I'm here for. Keep talking. And I'm so excited to do something interesting. Real interesting. Cool, yeah. All right. So, this is really, really, really important in chemistry. And can I take away from this just for a minute to look at the periodic table? If we look here at the periodic table, where on the periodic table are the things that just have a few electrons in their shells? In their outer shells? You know, 1, 2, 3, just a few where they might want to lose them. Yeah, yes, sir. Very good. So these things here, they tend to want to get rid of their electrons. So hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, beryllium, magnesium, calcium, strontium, scandium, yttrium, boron, aluminum. Those will tend to be the things you'll see. And even these guys. Even the metals are a long way away from having a full shell, so they tend to give away electrons. Does that make sense? Where are the things on the table that are really close to having a full shell, and they just want to get a few more so they can fill up those shells? The right side. So carbon, silicon, maybe sometimes, but nitrogen, phosphorus, arsenic, oxygen, sulfur, selenium, fluorine, chlorine, bromine, iodine. These are the ones that are always really electron hungry. They're trying to get electrons. Does that make sense? That's how this works. One of these guys, magnesium, could say, okay, I've got some electrons to lose. And fluorine could say, hey, I could use some electrons. They can make a bond. Does that make sense? Scandium could be like, hey, I've got some electrons to lose. And sulfur could be like, hey, I need some electrons. They could make a bond. Let me ask you, will calcium and potassium bond this way? Doesn't work, right? Doesn't work. Because calcium would say, hey, I want to lose some electrons, and potassium would say, hey, I also want to lose some electrons. Are you going to get a bond? Oh, it doesn't work. Does that make sense? Will oxygen and sulfur make a bond this way? Doesn't work, right? Because they're both trying to get. So this works well when we have something from this side of the table meeting up with something from that side of the table. And the further apart they are, the better it works, the easier it happens. Does that make sense? The closer together they get, the harder it is. And if they're really close, they can't bond that way. That's why you can find sodium chloride and you can find magnesium oxide, but you can't find calcium magnesianide. That's not a thing. It doesn't exist. It doesn't make sense. Because the calcium would want to give its electrons away, the magnesium would also want to give its electrons away. And what you need is something that wants to get them. Does that kind of make sense? Again, normally we'd spend like a whole day just talking about this, then we'd do some homework, and the next day we'd build some models, and then we'd do a lab. And then we'd spend a whole day talking about how we name that stuff. Then we'd talk about the next type of bonding, not how it's going today. So you guys are being asked to learn this stuff really quickly. So sorry, but well, that's where we're at. So make sure you pay attention because it's a lot and it comes quick. And if you don't follow along, you'll probably get lost. So let's try a couple. Show me how beryllium and oxygen could do this together. All right, I want you to draw me beryllium and draw me oxygen and show how they could make a bond together.
Can you smell it for a sec?
Yeah, I'd love to. All right. So beryllium and oxygen, fill in that space. I'll give you all, I don't know, 3-4 minutes to try that out. Ask me if you need help. Talk to each other. Draw it on paper. That can be really helpful. Draw it on the whiteboards. All right, try it. I promise you will not learn this stuff just by watching me do it. You gotta do it yourself. Gotta do it yourself. No way around that.
One?
Yeah.
No, two. Actually, you don't gotta scroll down. Just literally, I know, one below. Oxygen. Oh my god. D is a negative charge, right? What is a negative charge?
And then oxygen becomes negative.
What is oxygen negative?
Because it has more electron filling there.
So beryllium becomes positive, oxygen becomes negative. Right? Beryllium becomes positive and oxygen becomes negative. Yours looks a little more neat than mine. Oh my god, look at that. I can't tell what the mouse.
Beryllium and oxygen. Okay, cool. How's that going? Anyone got it? Anyone have any questions?
We both got it.
Do we need? Oh, yeah.
Hey. Oh. What's that? Wow.
Hey.
I can't draw it. My fault. Wow. I hammered it out.
Yeah. Oh, look at that. Good.
I didn't take part.
Good. The only thing is, only.
Music.
How many electrons did I get more?
Music.
How many electrons did I get?
Music.
The charges?
Oh, next.
No, you got to do the plus and minus. How many electrons did I
Next
get?
semester?
What's the charge plus? Yeah, you got it. You great job. All right, can we take a look here? Okay, talk to me about beryllium and oxygen. What's beryllium's chemical symbol?
BE.
Be. Hey, should I write that like this?
No.
Why not?
The second letter has to be lower.
Oh, lowercase. Okay, so like that.
Now, the first letter has to be
Uppercase. Okay, yeah, listen. Everything on the periodic table, the first letter is uppercase. Sometimes that's the only letter, in which case that's fine. But if there's a second letter, it will always be lowercase. So if you were to see something like that, you would know that these are two different atoms, right? Because uppercase always means the start of a new type of atom. Okay, good. So there we go. We have beryllium, and beryllium has, let's take a look. It's got 4 electrons altogether. But how many shells does beryllium have? 2 shells. It's got a full inner shell, but then that outer shell only has 1 and then 2 electrons. So if I'm drawing a Lewis diagram of beryllium, it should look like this. Did I put one below? Oh, I'm so smart, man. I'm hired. All right. And what am I asking to put this with? With oxygen? How many electrons does oxygen have? 6. Okay, so 1, 2, 3, 4, 5, 6. Okay, I think I know what happens, which is oxygen is going to give its electrons away, which will fill up beryllium's shell, right?
No.
I think it is. I'm the teacher and I'm drawing it.
No.
Why not? Why can't that? Could that? Listen, would that work?
It would.
It would work, so why can't I do it?
Oxygen wasn't the take.
Yeah, because can I tell you that sadly, nature provides the way that unfortunately we see all too often in life. In life, and this is the sad truth, and you will find it, the rich get richer. It is not those who have more who give more. There may be people in the world who tell you that's how it works, but if you just look at the numbers, it is not. The reality is that entropy, nature, things working the way they work, tends to be the case that those who already have the power to take more. The way this works, the way the chemistry of it works, is that oxygen has more pulling power on electrons than beryllium. That's why it has more to begin with, and that's why it's going to get more. You'll learn a bit more about why that is in grade 11 chemistry. You'll learn even more about why that is in grade 12 chemistry. For now, you just got to trust me. But thank you for correcting me. So beryllium is going to give this electron away, and it's going to give this electron away. Cool. Does that work?
Yes.
Yeah, that example works nicely. And the result, what does beryllium look like now? Does it have any valence electrons? No, I mean, you could think of the shell below it as being there, but what used to be its valence shell is now empty. Hey, it lost 2 electrons. What must be true about it now? Positively charged. How positively charged? By 2, because it lost 2 electrons. Hey, what do I put around this to show that it's an ion? Yeah, we always show it in square brackets. That's just a convention. Doesn't really mean anything, but it's how we do it. Hey, what's oxygen look like now? Well, it has its original 6 electrons. And now it has another one here and another one there. What will be true of it now?
Negatively charged.
Yeah, how negatively charged?
By 2.
Negatively charged by 2. And these will be stuck together. These are now in what we call ionically bonded. And the way we would write that is we would write it as BeO. Makes sense, right? This is now what we call beryllium oxide. I'm not going to make you worry about naming this year. You'll get plenty of that to worry about next year. It's easy. You just change the N to "ide." But anyway, beryllium oxide, BeO, is what you get when you put these together. Be and O come together. Hey, what would the formula of this example have been? Na and Cl come together. Now it's going to be NaCl. And what would we call it? Na is sodium. Yeah, very good. All we do when we name these things is we change the ending to "ide." You don't have to know that, but it doesn't hurt to hear it, because then you'll kind of know it. And next year, when you have to know it, you'll be good. Do we have time to do that? I just want to show you really quickly, and you don't even have to write this, because time being what it is, we're not going to get into this, but sometimes you might get a case where, what if we put sodium with oxygen? Sodium has how many electrons in its outer shell? 1. And oxygen has how many electrons in its outer shell? 6. What if we had something like this, where if sodium gave its electron away, is sodium happy now? Yeah. So sodium is like, hey, look at me. I'm a stable ion, and I have a charge of +1 because I gave my electron away. Is oxygen yet stable? Oxygen would have 1, 2, 3, 4, 5, 6 of its original. That's got this red one, but it's not yet stable. What would I need to make this work? I would need another sodium. And I'm going to show this one with a blue electron just to show. So just to show you, sometimes you need more than one. Oh, I shouldn't have drawn. I'm being consistent here.
Where do I draw this?
You can make a little space under here if you want. You don't really, I'm not going to give you complex examples like this for now. But you can. It wouldn't hurt. Now we have another sodium, and this oxygen, what's its charge? Negative how much? 2, because it gained 2 electrons. Does that make sense? So that can happen. Again, this is really more grade 10 chemistry. You don't have to get into that, but I just want you to be aware that it's not always a nice one-to-one relationship. In this case, sodium's only able to bond with oxygen if for every 1 oxygen we get 2 sodiums, but it still works. Lots of atoms around. So 1 sodium atom wouldn't be able to make this work, but as long as you have 2, you're fine. What would the formula of this be? How would we write that? Na2O. And that just means you need 2 sodiums for every oxygen, and you still just call it sodium oxide. So if you want to draw that, nothing wrong with drawing that, good lesson. But for this year, if you get the concept, if you get the idea of giving and taking electrons, I'm fine with that. Don't worry. Next year, I will make you very good at finding the formulas and finding the names. You'll be a pro star. You'll be like, wow, I didn't know I could be such a pro star. So really the important thing this year is to get the idea, to get the concept. Do we feel like we have the concept? Okay, now we said this works really nicely for certain things on the periodic table. I want you to try to do this with oxygen and fluorine. So take a minute and draw me Lewis diagrams for oxygen and for fluorine. Okay. Just so I know, does this go 1245? Is that my number?
Yes.
Okay, we'll make it. Whew, it's going to be tight today, but we'll make it.
How's this gonna work? They both, exactly. They're not giving A1.
Exactly. Precisely. Okay, let's take a look. Oxygen. How many electrons in its valence?
6.
So 1, 2, 3, 4, 5, and 6. Okay. And fluorine. How many electrons in its valence?
7.
7. Okay. 1, 2, 3, 4, 5, 6, and 7. Okay. Here's the thing. Remember how we said the rich get richer in electron terms? And when they come across a poor atom, they are able to take their electrons from them. It's a kind of a sad analogy. I don't like it, but it really is a pretty apt analogy. Here, oxygen is pretty electron rich. Fluorine is pretty electron rich. They both have a lot. Is fluorine going to start giving all these away? Not a chance. It's already pretty much got a full shell. Is oxygen going to start giving all these away?
No.
Not a chance. It's already pretty much got a full shell. So what can they do?
They can work together.
Good. They can share. They can work together. And this is literally what it works. Basically, it works like this. We said, okay, listen. I need another electron to get a full shell. You need another electron to get a full shell. What if we decided to say between us, we have a pair of electrons that we both own? And they can spend half the time with you, and they can spend half the time with me. And so they can do that. Oxygen and fluorine can there's an arrangement where this pair of electrons becomes a shared pair of electrons, which means that they orbit both atoms. And because they orbit both atoms, they can do so in a stable way. Now, I want to be clear, this requires a lot of kind of just a leap of faith. You just kind of have to trust me that the chemistry works on it. Because it's a little weird, right? But they share. And now from fluorine's perspective, how many electrons does it have? 1, 2, 3, 4, 5, 6, 7, 8. This fluorine is now stable. Does that make sense? Hey, is oxygen stable yet? 1, 2, 3, 4, 5, 6, 7. What do we need another of down here? We need another something else. And what would work just fine? Another fluorine would work just fine. Because if we had fluorine down here, it could have... How many electrons does fluorine have again? Yeah, and I wish I hadn't picked oxygen and fluorine as my first example. That wasn't the wisest thing I've ever done, but that's okay. Because we have to show you 2. So that's a shared pair. And if we look here, now, how many electrons does this fluorine think it has? Well, 1, 2, 3, 4, 5, 6, 7, 8. Is that fluorine stable? Yeah. How many electrons does oxygen now have? 1, 2, 3, 4, 5, 6, 7, 8. Is it stable? Yes. They all have what we call a full octet, or a full valence shell. So, what we end up with is oxygen, fluorine, and fluorine. And 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 6. And we end up with this arrangement. Hey, what would be the chemical formula of this? By the way, when you make a chemical formula, always start on the left side of the periodic table. We put them kind of in quote-unquote alphabetical order. We start with things further to the left and then put things further to the right. That's just a convention, but it's one we usually follow. So the O would usually come before the F. If you wrote it with the F first, I wouldn't really care, but that's kind of good manners. We usually go from left to right. So what would the formula of this be? Well, how many O's do we have? Just the one. But how many F's do we have? 2. So that would be the chemical formula for this. Does that make sense? Awesome. We'll talk about the naming of this in grade 10. Covalent compounds are way more interesting than ionic compounds. Sharing ends up being a much more interesting way of doing things than just giving and taking. So the naming is more complicated too. This is actually called oxygen difluoride. You have to tell me that there's 2 fluorines. But don't worry about that. You don't need to know that. Not this year. But if you've heard of like carbon dioxide or, carbon monoxide, you know that we can use those prefixes to say how many of everything. Don't worry about it too much. Okay, so what we're going to write then is this. Atoms that have almost full shells won't lose electrons. They will share electrons with other atoms to form full shells if they can't take. This is called a covalent bond, which is actually a really good name. Because you know what co means. Like, what does it mean if you are the co-owner of something?
You're a part owner.
Yeah, you own it with that person. You own part of it, they own part of it. What does it mean to say that 2 people co-parent? Like you might not be like married to or partners with or living with the other parent of your child, but if you say you co-parent that child, it means that you're both parenting that child, right? What does it mean to say that you are like, you cooperate with somebody?
You work on the same thing together.
Yeah, you operate with them. You both operate something together. You work together. So this is called a covalent bond. And so it means, covalent means that electron belongs to both valences. If we look at beryllium and fluorine and oxygen, these electrons belong in fluorine's valence and in oxygen's valence. They're covalent. They're shared. They sometimes call this a molecular bond, too. That's the other word you'll see. Covalent bond or a molecular bond. Yeah, I'd love to. How is that? You're only going to see this kind of bonding on the right side of the periodic table, the far right of the periodic table. Only the rich do this, all right? You can kind of think of it like the electron rich go into business together and share, and they make money together. But if one of those electron rich goes into business with one of the electron poor things over on the left side of the table, do they share? No, they take. Does that make sense? They will always take if they can, but if they can't take, then they will share. All right? Again, kind of a dark analogy. I don't love it, but it works.
They become positive. They become happy.
Well, there might be something to that. Yeah.
It's kind of scary how much this connects to other things, like things like
Yeah. Like not just a metaphor, maybe, but like.
it's pretty much gravity.
Yeah. Well, it goes to show that like the forces that govern the universe are the forces that govern the universe, and that's true. It's true in math. It's true in physics. It's true in chemistry. But it's also true on a broader scale. It's true. Like, keep in mind that like people are. You zoom in far enough, and you're molecules, right? You're molecules following rules. You're not just molecules following rules, but you are molecules following rules. So there we go. That's a philosophy lesson for a different day, though one I'd be really interested in talking about. I couldn't be the teacher on that. I don't know enough, but I'd like to be a student. be interesting to learn about. So these are the two ways we form bonds. Again, normally this would be like 2 whole weeks of learning. Like we'd do a whole week just on ionic bonding, and we'd build models, and we'd do labs, and we'd do examples, and we'd go, wow, cool. And then we'd do a whole week on covalent bonding and naming them and building models. This has got to be truncated, and I'm sorry about that. But again, don't stress about it. If you like chemistry, and you should, because it's great. Because can I tell you something? Chemistry is like magic, but, and here's the thing, it's real. It's all real. You can really do it, which is just crazy. So if you like chemistry...
But you're saying magic is...
I would never say that. If you like chemistry, you get a bit more of it in grade 10, and that's fun too. But then in grade 11, you can do a whole course which is just chemistry. And then again in grade 12, you can do a whole course that is just chemistry. Great courses, great classes, highly recommended. And not just because if you take them, I still have a job. Though, if you take them, I still have a job, which is good. I don't have to like become a French teacher or something. That wouldn't go well. I would not be a very good French teacher. Okay, now the thing about sharing is there's lots of ways you can do it. There's not just one right answer. For the ionic questions, there's only one right answer. There's just one way they can give and take. Sharing can end up playing out a lot of different ways. But I'll give you a nice, easy one. How could hydrogen might be confusing. How could 2 fluorine atoms, the 2 chlorine atoms, how could 2 chlorine atoms become stable? Draw that below. How could 2 chlorine atoms, which are not stable, become stable when you put them together? What could they do? Try it out. See what you come up with. Why do you know what metals taste like?
What metals is blood from their mouth?
Alright, focus.
Wow, Gordon.
No, you're not. I just looked at stuff.
Did your wife not just go maybe not show my nipple to the
It's not me. I'm not the one taking all this. But like, how you gonna learn stuff? Have focus. Good Lord. Good Lord.
Well, I'm mad that you so naturally shit me
I thought I already recorded that. And then when kids come up to me, I'm just gonna be like, one sec, I take out my phone and be like, and play. I like that. That was good. I'm gonna do like a recording session. I'm gonna get you to say all things like, get to work!
I see
forward! Yeah. Oh, can I show you?
Go out, go left. You know where the gym is?
Yeah, go ahead. You bet.
What?
You betcha. Yeah.
Yeah.
You got this done? What do you mean maybe? That's not an answer. It's a yes or no question. Maybe. Maybe I'm about to freak out. I don't know. Maybe.
I didn't get to write down this one exam for that. So this is all I know to do.
Oh, do you want me to scroll up?
Oh, I keep accidentally drawing lines over my page.
There you go. No, you did. You literally did it perfectly. That was a good job.
It's not the worst, but it's not the best.
Okay, I think this is good. So, you got chlorine atoms, chlorine. Awesome. Wait. Now it's another. And it's chlorine. Now, what is our dot diagram? You know how many atoms? That for me?
Oh, look at my old one. It's not that bad, but it's still laughable.
Can I give you advice? Let me do like easy. Let's take this one. Why did I suggest that? I don't know.
I can tell from the handing, but I've calculated every single possibility of here.
I don't know. I'm sorry, I haven't been paying attention because I've been so
I'm not even going to say that. I'm going to suggest you're totally right, but this is good. But to make life easier, let's take that one and just write that one.
What?
Okay, so we've got two chlorine atoms. What could they do so that they both be stable? Are they going to give and take? Like, will this one start giving away? No. And how many would they have to share in this work? Yeah, right. Well, we just know that. Just say if they share just one each, and sure, they always give one each, right? Like it's always pairs. Because I'm not going to share with you nothing is pairs, right? So they both also one of them shares a while you now this chlorine, as far as it's concerned, has one. And this chlorine, as far as it's concerned, has 1, 2. Does that make sense? You use camera.
Why they let them on?
Whatever. Alright guys, can we take a look at this? Because time's on a bit short. Let's take a look. Let's take a little lookaroo. So, what did I ask you to put together? Now I feel really tall.
Whoa.
This is nice.
How tall is that?
You were actually my dad.
I really wish I were this tall. That would be nice.
You look so weird right now. You remind me of my dad.
Okay, so, what did I ask you to put together? Two chlorines. What's symbol for chlorine? Cl, like that?
No, lowercase.
Like that? You said lowercase! Make up your mind! What is it?
Uppercase C and lowercase L.
Oh, okay, like that? Alright, good. I feel like we've made an understanding with one another. I apologize for shouting. Okay, so, what should I do if I want to know how these will come together? What should I do? No, I think I would probably hurt myself.
Do it.
I think there's good odds I hurt myself getting down from here. So what should I do? Draw the electrons. Okay, how many electrons does chlorine have? 7. Okay, so I should go like 1, 2, 3, 4, 5, 6, 7. 1, just like that?
Well, you could.
I could if I wanted to make my teacher sad. If you wanted to see me weep, you could do that, so please don't. How do we normally draw them? What's the convention?
North, east, west.
Yeah, 1, 2, 3, 4, 5, 6, 7. And I'm going to be kind of strategic, and I'm going to leave the empty one kind of facing this way, because I figure the action's probably going to be over here. And how many electrons does this chlorine have?
7.
Yeah, neutral chlorine atoms always have 7 electrons in their valence shell. We know that from its location on the periodic table.
Hey everybody, if the teachers could please submit their group results.
I'm talking here! Willem, I better win if you interrupted me. I guess he interrupted everyone. That doesn't really make sense, but I just want to win.
I want to submit those because I think most of us did more.
Oh, I submitted, and we better have not done horribly.
I got one.
Okay, I know you. Listen, we're 32 seconds away. How do these form a stable ion? What do they do?
Sharing is caring.
Yeah. They share, and then look. From this chlorine's perspective, it has 1, 2, 3, 4, 5, 6, 7, 8 electrons. Stable. This chlorine has 1, 2, 3, 4, 5, 6, 7, 8 electrons. Hey, what would the formula of this be? Cl2. Hey, that's chlorine gas. It's reasonably stable. It's not super stable, but it's a lot more stable than chlorine by itself. So there we go. Listen. Normally this would be followed with a week of consolidation. Do I think that you're going to have this cemented in your brain forever and next year we'll come back and you'll have this totally right where we left off?
I have short-term memory loss.
No, probably not. But that's okay. Listen, if you understand the concept that atoms can be either made stable by giving or taking electrons or by sharing them, whichever works, if you come into grade 10 with that concept understood, you'll be great. You're going to be in good shape. You'll be fine. We'll get you knocked into shape in no time in grade 10. All right? Can I do a quick poll? Because I'm actually cool either way. I have a lab set up for 4th period. It doesn't have some big write-up. Every single thing you're going to write up for it is something you'll just do during the lab. I think it's pretty fun. You get to light some stuff on fire. Or, I am also perfectly content to just give you the period to get caught up on stuff. I'm not trying to make work for you, but I do think it's a fun, cool one. I'd like to do it, because I think doing labs is fun. But I guess what I'm going to say is this. I'm not going to do it by show of hands, a vote or thing or like this or that. My plan is to go to a lab after this break. If you feel strongly the other way, come talk to me during this break, and if enough people have done that, then I will adjust my plan. You don't have to out yourself. But just if you're like, hey, I really need some time, let me know. If a couple of people say that, I might even say, hey, you're cool to just do what you're doing. Okay? But other than that, we're going to head to the lab after this break.